Hopefully, your eyes lit up when you saw this function cos x times ln sec x, and we've got this graph. Right, well, let's find some stationary points. A and B are maximum points. Find the coordinates of B in terms of E. Well, I'm very tempted to write sec x as cos x to the minus 1, and then bring that minus 1 down. So y is actually equal to minus cos x times ln cos x. And if I differentiate, it just feels a little bit easier. dy by dx equals, I'm going to have to use the product rule here. So I'm going to differentiate minus cos x, which will give me sin x, times that by ln cos x. And then it's going to be minus cos x. I realize there's no way I'm going to fit that in. Minus cos x times, now it's ln cos x, so I'm going to differentiate kind of ln x, which gives me 1 over x. It's going to be 1 over cos x, and then times by the derivative of cos x, which is minus sin x. So first of all, these cancel, and then the negative is going to become a positive. So I'm going to have sin x 1 plus ln cos x. This will give, or stationary points equals 0 for stationary points. So sin x equals 0, which will give x equals 0, and actually that's it, because we're only interested in minus pi over 2 to pi over 2. We've just found this stationary point. Or ln cos x equals minus 1, this right-hand bracket, which means cos x must equal e to the minus 1, and hence x must equal inverse cos to e to the minus 1. Or actually, let me write it as 1 over e. So that is going to be our value. Now this will lead to two possible values, the a and b. So the one we're interested in is the positive one. Now when x equals inverse cos of 1 over e, y will equal minus cos x ln cos x. So minus cos of this will just be 1 over e. And then ln of cos x, well, it's cos again of inverse cos, so ln of 1 over e. So that will actually cancel ln. Let me just put an extra step in. It's going to be 1 over e ln e to the minus 1. I can bring that minus 1 down and cancel it with that minus. Ln e is just 1, so I get 1 over e. And therefore b has coordinates the same as a, in fact, except we're just going to get a different inverse cos value. Okay, nice start to this question. On to B. We're told that the finite region R lies between C and the line AB. So that's the line AB. So we are interested in this bit here. That's going to be R. And we have to show that the area of R is this thing here, okay, which looks ridiculous, but it's all going to come out the maths. What we know is essentially we have a box, a rectangle, and remember the height, that was our value of y for the b, that was 1 over e, and this distance here Well, here to here, remember, was inverse cos of 1 over e. So it's going to be 2 inverse cos of 1 over e. That will give us the rectangle, and so that just leaves here and here that we have to find, so we can subtract that. And these red parts are going to be the same, so I don't need to integrate from this value to this value. I could just go from 0 to inverse cos of 1 over e. Okay, so I'm going to, how do I put this together? R is going to be the rectangle, so it's going to be 1 over e times 2 inverse cos of 1 over e minus the integral. We can just say it's going to be 2 lots of the integral of this. I'm going to stick with this function, I think, rather than the sec. 2 lots integrating from 0 to inverse cos 1 over e of minus cos x ln cos x. That gives a double negative, so I can actually, maybe I shouldn't do too much too quickly. I'm also slightly frustrated I can't quite fit this in, so let me give it one more go. It's a double negative, so I can change it to plus. And it is worth just having a little peek every now and then at what we're actually trying to get to. The good news is we've got that first term, so we just need to get these second two terms out of this integral here. Let's take a look at it without the limits. So cos x ln cos x. Now, it might be tempting to try and use substitution for this, but the derivative of cos x isn't going to somehow cancel out with this cos x, so that won't be a productive path. And in fact, we have, we've kind of differentiated ln cos x earlier, like it's not too bad. So this is going to be our u, and this is going to be our v dash, as opposed to trying to integrate the ln cos x. So u dash will be, well, I'm going to get 1 over cos x, and that'll be times by the derivative of cos x, which is minus sine x. And then v will be the integral of cos x, which is sine x. We don't bring a negative in. It's when you differentiate cos x, you get the negative sine x. So I'm going to get sine x ln cos x. I've written it the other way around. It's just feels a bit more natural to write it like that. Then minus u dash v. There's a double negative in here, so I'm going to change this to a positive, and it's going to be, well, let me just write it as sine x over cos x times sine x. And in fact, it's not like I can make it sine squared over cos x and make it simpler. I'm going to change this to a tan x. And then we're going to need to do another integration by parts. So I'm going to make the tan x u now and the sine x v dash. Integrating tan x, we kind of want to try and avoid it. You get a ln going on in there. It might be that that's what needs to happen, but let's try it with u because it's easier to differentiate tan than to integrate it. So sorry, let me make this clear. I'm now just dealing with this part. I'm going to get u dash as sec squared x, and v is going to be minus cos x. So uv will be minus cos x tan x, and then I'll need sec squared x times minus cos x. And I've just realized that, sorry, I should have put a negative in there, minus the integral of u dash v, but in fact, I've got double negative, so these are going to cancel out. And what I also have is a sec x and a cos x, so they're going to cancel out, and I'll just be left with the integral of sec x dx. Now this is an awkward one. It's one that is worth knowing, in fact, because it is not easy to just do this from scratch, like especially if you've never seen it before. And in fact, it's actually plus ln sec x plus tan x. Try and learn that if you haven't already. And of course, we're going to get a plus c finally. So therefore, I'm now going to bring the limit in. I know I haven't quite brought it together, but it was this cos x ln cos x. And equal to that first term, sine x ln cos x. And then we're adding this integral, so I'm going to be minusing cos x tan x, and then adding ln sec x plus tan x. And remember, we don't need the plus c now because I'm actually putting the limits. Now I'm going to jump straight into this. Actually, sine x, this is an awkward one because we don't want to find sine of inverse cos. We want to change it so it's in terms of cos. And sine squared is 1 minus cos squared. So sine x is then the square root of 1 minus cos squared x. So we just got that in the back of our minds. So I'm going to get, instead of sine x, I'm sine of inverse cos of 1 over e. I'm going to get 1 minus cos squared of inverse cos 1 over e. And in fact, cos squared of inverse cos 1 over e, or the cos and the inverse cos will cancel out, and I'll just be left with squaring the 1 over e. So basically I've replaced the sine x by this. Maybe I should just show a little bit more explanation. So sine of inverse cos 1 over e is equal to 1 minus cos squared inverse cos 1 over e, all square rooted. And what I'm trying to say is the cos and the inverse cos are going to cancel out. Remember, I do those before I then square it. So cos of inverse cos just disappears, and I'm left with then squaring it, so it's going to be 1 over e squared, like I just put. Just trying to explain where that was coming from. Then it's going to be ln cos of inverse cos 1 over e. Again, that's just 1 over e. and then minus 1 over e, because it's cos of inverse cos 1 over e. Then I've got tan x. Well, that's going to be sine x over cos x. So I can write square root 1 minus 1 over e squared for sine x, all over cos x, which is 1 over e. These two will cancel. Let's keep going. Plus ln sec x. Well, cos x, remember, is cos of inverse cos, 1 over e. So sec x is just 1 over that. So it's just going to be e. And then I'll be left with this again. Tan x is going to be this 1 minus. This is not particularly nice, is it? Let's be honest. When I substitute 0 in, because sorry, I've just realized I made a mistake. Why did I change? Why did I make that e? This should have been 0. That was my limit. I'm going to put in sine 0. I'm not going to get anything here. Tan 0 and ln of 1 is also 0, so I don't get anything coming from that. So that's probably worth at this point just seeing what we're actually trying to get. We're trying to get this over here. So let me copy the whole thing. Now remember, we've already got this part, and we're adding 2 lots of this integral. This was from before, and I'll have to actually add 2 lots of this integral that I have here. So let's just take a little look at it. All right. We've actually got a kind of a common. Okay, so ln of 1 over e is actually minus 1. So this, I can write minus 1 here. Just cross that out. Now I also have the same term here. Because these cancelled out, I've actually got 2 of them. They're both negative. So I'm going to be adding 2 lots, because remember, it's 2 lots of the integral that I just found. 2 lots of minus this thing here. But actually it's 2 lots of minus 2 lots of that, because I've got this one and I've got this one. So I've got 2 lots of it. I'm just timesing by 2 because that was in my original integral. And then I'm adding ln e plus, and because I'm dividing by 1 over e, that's the same as timesing by e. So it's going to be e 1 minus 1 over e squared. Just be really careful manipulating it. At least we've got the answer to try and get to. So I'm clearly going to get this 2 ln e plus. Right, now when I times through by e, this bit here is going to be the square root of e squared. When I bring it into the square root, I have to square it. 1 minus 1 over e squared. So essentially, this is going to partially cancel, and I'll be left, well, no, sorry, I'll do e squared times 1 to give me e squared, and then the e squared and the minus 1 over e squared will cancel, so I'll be left with minus 1. I'm just justifying where this has come from, but that is correct. Now I've just got this last term, minus 4 from here. And it looks like they factor in a similar way to how I times by e, they've actually factorized out an e. So I'm just going to go straight for it. I can write it as 4 over e squared minus 1. So what I've done is essentially I've times this by e, which means I've times the square roots bit inside by e squared, which gives this. But of course, I can't just times by e, so I have to divide by e to make it equal. But I hope I've been comprehensive enough, convincing enough. That is our final answer. Good question. It's got to be said, a lot going on in that question. Um, we think back to part A, that wasn't too bad, was it? We had to find the area of the rectangle, but then the main thing was finding this red area. In fact, just one of the red areas. This is like the literally the hardest part of the question, finding this red area, because then we doubled it. We had to integrate the function, which meant that we had to do the well, first of all, we wrote all this down. Then we used the product rule. Sorry, not product rule, integration by parts. We got this. We had to use integration by parts again. And then we had to integrate sec x and remember what that was. And then we had to put in all these limits dealing with the inverse cos 1 over e using this identity. Simplify it all down to this nice answer. Okay, well done.